So let me start. So we started towards the end of last lecture in the last couple of minutes to discuss something new, something which I will want to call conformal dualities. Okay, let me go very quickly over what we have discussed in the last 5-10 minutes of the last lecture, and then we will go to use this notion of conformal dualities together with notions from geometry. Okay, and today, finally, the geometry part of the title of this series of lectures will enter to the discussion. So the picture I want to have is like that. So say we have some theory, again, as I discussed last time, somebody hands me some theory, let me call it T1, and this theory has a lot of exactly marginal deformations. Okay, maybe 1, maybe 120, some number of exactly marginal deformations. So the space of exactly marginal deformations I will call MC. And this theory doesn't have to have a Lagrangian. I don't ask for a lot from this theory. I just want some information about it that I will remind you what I want soon. The question I want to ask is whether there is another description of this theory somewhere else on this conformal manifold. Okay? There is some other point on this conformal manifold, and the theory there, let me call it T2, so that these two theories share the same conformal manifold. What does that mean? That means that any other theory on this conformal manifold, say T3, I can think of it as T1 plus some exactly marginal deformation. I can approach it by starting here and then tuning some couplings and going here, or as a T2 plus some exactly marginal deformation. Okay? So the same point has two different descriptions. So you can ask, if you have a conformal manifold, it is a manifold, it has an infinite number of points, so I can start from any point and go and describe any other point by the formations of that random point. So what I want is the following. So this theory is abstractly given to me. Okay, it's something that I have no control over. But I want to have a useful description of this T2. For example, what we will do, we will look for T2, which has a Lagrangian description in terms of free fields, free chiral superfields, and free vector superfields. Okay? One example of such a duality, of a conformal duality, you all know. So again, this is a conformal duality because no flow is involved. We have theories, many theories, which are connected to each other by continuous deformations. And maybe I have two different descriptions that I can come up with of any theory on this conformal manifold, maybe more than two. We will see examples. Okay, so an example that you know, or many of you might know, is that of n equals 4 super Young-Mills. Okay, n equals 4 super Young-Mills with, say, SUN gauge group has a conformal manifold. And it is, on this conformal manifold, you can have various weakly coupled cusps, okay, where you have a gauge theory description. So one way to think about n equals 4 super Young-Mills, say, with SUN gauge group is with this Lagrangian, but there is another way to think about it as a theory with SUN mod Zn Lagrangian. Okay, so and these are dual to each other, these are conformally dual to each other. So this is a simple example, and we want to find more examples as a first step, and then we will use this technology to discover something interesting. Okay, so let me, I will try to fit it on this blackboard, the algorithm to fit, the algorithm to look for such conformal dualities. Again, I mentioned it before. So the first thing I will want is that somebody to give me some information about this theory T1. For example, the thing that I will demand is that the person will provide to me with A and C anomalies. That the person who gives me this theory will tell me what is the symmetry which is preserved generically on conformal manifold of this theory. When we have a theory and we deform it by some deformations, and here we have exactly marginal deformations, with some deformations, we can have bigger symmetry than with others. So some deformations might break some symmetry, some might not break some symmetry. But when I mean this symmetry GF, I mean the symmetry on a generic locus of the conformal manifold. Okay, so like the minimal symmetry that I will have on the conformal manifold. I will ask for 't Hooft anomalies for these symmetries. Okay, and if the person is very kind, I will ask also for various other bones that the theory might have, such as indices and so on. Okay, so these properties are independent of the continuous parameters, and I can call them MC invariants. Like these are invariants of the conformal manifold. If I compute them here for some theory T1, the theory T2, if I can compute the same quantities in theory T2, they should be the same. Okay, so this is the basic idea. And then there is an algorithm, and the algorithm is extremely simple. So the step one of the algorithm, I just take these quantities A and C that the person provided. This is the absolutely minimum thing that I want to be given. And then I assume that there is a Lagrangian description of this theory T2. That means that the R charges of all of the fields that build this theory are equal to 2/3. Okay? I also assume that the theory is conformal, so I will assume that all the beta functions for all the couplings, gauge couplings, superpotential couplings, so all are 0. Okay, so I have 3 vectors and I have 3 chiral superfields there. Using this, we can immediately write an ansatz for A and C. The A of this theory is just given by the contribution of all the 3 chiral fields. So we have A chi times the number of chiral fields, and all the vector fields, AV times NV. And again, these numbers are just given. We assume that it is a free theory, so they can be computed with this value of R charge. So the only unknowns in this equation is the number of chiral fields and number of vector fields. And the C is given, again, by C chi times N chi plus CV times NV. And again, C chi and CV are given, N chi and NV we need to fix. These are 2 equations for 2 variables, so we can extract from it these numbers, the number of chirals and number of vectors. As we mentioned last time, if these numbers, so from here I deduce N chi and NV, if these numbers N chi and NV turn out to be fractional, it means that the conjecture that somewhere on the conformal manifold of theory T1 we have a Lagrangian description, that conjecture is wrong, okay? So that cannot be. If these are integer, we are continuing our search. So what we do, we now look for conformal Lagrangians with NV vectors and N chi chirals. Okay? It might be that we will not be able even to find a Lagrangian with this number of vectors and this number of chirals, even if they are integer, a Lagrangian which is conformal. Okay? That means that all the beta functions are 0. Say we found a Lagrangian which is conformal. We continue to the next step. In the next step, we analyze this Lagrangian. In particular, since we have a Lagrangian, using the various techniques that we have already discussed, we can deduce what is the GF and what are the 't Hooft anomalies and what are the indices of these theories that we obtained. So here we basically obtained some collection of theories. Let me call them T tilde I. Okay? So it might be, this collection might be empty. Okay, so then that's it. Again, we ruled out that there is a Lagrangian description. It might have one theory, it might have 2, it might have million theories, but that set will be a finite set because there is just a finite number of conformal theories we can write with given number of different fields. Okay? And then after we have computed these additional bounds for these theories, we compare them to what was given to us. Okay? If we find an agreement for all of these quantities, we are happy. We come up with a conjecture duality. Okay? And after we conjecture duality, we can try to disprove it in various ways. We cannot, with the techniques we have at the moment, we cannot prove dualities. Okay? To prove dualities means that we need to check everything possible, or to find, if both theories have a Lagrangian, we need to find a change of variables, which brings us from one to another. This typically does not happen. If that happens, the duality is typically not interesting. Okay, so we can try to disprove the duality by performing various consistency checks. Okay, so this is the basic algorithm. It's very simple, and it fits on one blackboard. So what I will do first, I will discuss a very concrete example of applying of this algorithm. And I will do it almost in complete detail. And then we will discuss other, in a sense, more interesting examples, which will be related to geometry. Okay, so that's the plan. So let me start with first example. Okay, in this example, somebody gives me the theory T1, okay, and this theory is a Lagrangian theory. It's a weird theory. Maybe you never looked at such a theory, but it's a theory. Okay, so the theory I will consider has a gauge group which is G2. Okay, so you might want to start with more vanilla groups like SUN or whatever, but you can do that. But actually, the simplest example that I know of application of this type of algorithm is with the group which is G2. G2 has an adjoint representation which is 14-dimensional. Okay? So the number of vectors this theory has is 14. Okay? The theory I will consider will have 3 fields in the fundamental representation. A fundamental representation of G2 is 7-dimensional. So this representation I will denote it by 7. Okay, so I will have 3 fields in the 7-dimensional representation. And I will also have another field, which I will denote by this dotted line, which is 27-dimensional, in 27-dimensional representation of G2. That's it. Okay. The 27-dimensional representation appears in a symmetric squared of 7. If you take this fundamental representation, you do symmetric square, you will get a 27 and a singlet. So it's if you wish, it's a symmetric to index representation of G2. Okay? So this is my theory T1. Okay? So first, I need to show you that this theory is conformal and compute various invariants of this theory. Okay? So I need to give you, the first thing I need to give you is A and C. These are A and C anomalies. But actually later on, from these A and C anomalies, I will need, the way I use the algorithm, I will need to derive the number of vectors and the number of chirals. But since this theory is already Lagrangian, I know what the number of vectors and number of chirals is. I can, translate them into A and C and then translate back to number of vectors and chirals, but that is pointless. So I will just tell you that the number of chirals you just count. You have 3 fields in 7-dimensional representation, so that gives you 21, and you have 27, so in total, the number of chirals is 48. Okay? And after I will deduce all the invariants of the conformal manifold, what we will do, we will look for another gauge theory, which sits on the same conformal manifold as this theory. Okay, we will look for a conformal dual of this theory, okay, systematically. Okay, so before we start, let me compute the beta function of this theory. Okay, to compute the beta function or to decide whether it is conformal at all, or it flows to something in a non-trivial way, or it is this gauge theory has a relevant gauge coupling, and then it is a free theory. I need to compute trace R G2 squared. Okay, this anomaly, and this is easy to compute. Okay, so first thing we have the contribution of the gauginess of G2. So remember that the R charge of each one of these gauginous is 1. And this index trace G2 squared of an adjoint representation is 4. Okay, this is some group theory fact. Okay, so trace of G2 squared in adjoint representation is 4. Then we have the fundamental fields. For fundamental fields, this group theory number, this trace G2 squared is 1. And then we have the contribution of the R charges, which is, again, as we computed before, is 2/3 minus 1 times 3, where 3 is the 3 fundamentals that we have here. And finally, we have this big field in the 27-dimensional representation, and its trace G squared is equal to 9. And again, it's a free field. So it's 2/3 minus 1. So you sum up all these numbers and you get a 0. Okay? So the gauge coupling of this theory is marginal. If we wouldn't have added this field, it would have been relevant, for example. Or if we would have less fundamental fields. Okay? So this matter content is fine-tuned so that the theory will be that the gauge coupling will be marginal. Okay? Now, what are the symmetries of this theory? Okay? The symmetries are, there is an SU3 rotating the fundamental fields, and there is an additional U1 under which the fundamental fields are charged and the field in a 27-dimensional representation is charged. Let me call this field Q and this field Q tilde. So there are 3 fields Q. So I runs from 1 to 3. So we need to assign this U1 charge to fields Qi and Q tilde, and the charges that we will assign are as following. So the charge Q of the field in 27-dimensional representation of Q tilde, we will choose it to be +1, and the charge Q of each one of these Qi's will be equal to -3. Okay? Again, these numbers are not random. They are chosen so that this symmetry, this U1 symmetry with these charges will not be anomalous. Okay? How do I determine that these charges are not anomalous? I compute the anomaly trace of this U1 with these charges, again, G2 squared. Okay? So again, the computation is very simple. So we have the contribution of these fundamental fields, and this is equal to 1 times the charge minus 3 times the 3 fields. Okay? And then we have the contribution of the field Q tilde, which has, again, this trace G2 squared is equal to 9, but the charge we chosen to be 1. So this sum is equal to 0. Okay? This is just a choice of a non-anomalous symmetry. Okay? So again, this theory has SU3 times U1 global symmetry, and the gauge coupling is marginal. Okay? So now we need to understand whether this theory has a conformal manifold. Okay? Whether this theory is the theory like that, with some exactly marginal deformations that we can turn on, or this theory is actually free, okay, that we cannot turn on any couplings, and we just are stuck to a free point. Okay, to do so, we need to turn on, in addition to gauge couplings, some superpotentials, which are marginal. We need to list all the marginal superpotential couplings, and then understand which of these couplings are exactly marginal. Okay. So what are the couplings that we can turn on? So what is the most general superpotential that we can turn on for this theory? Okay. So anybody has ideas what we need to do? Yes? Sorry, I didn't. Yes, we need to turn on some most general cubic couplings, cubic superpotential terms with this Q tilde Q, but these couplings have to be gauge invariant. So to really do that, you need to know your G2 group theory. Okay, I'm not sure how much of G2 group theory you know, so I will just tell you what these couplings are. There are actually many things that you can do. For example, we can turn on something with coupling that I will call lambda 0, and then epsilon ijk, qi, qj, qk. So this type of baryonic operator from the fundamental fields. The antisymmetric cubic of 3/7 of G2 has a singlet. So this is a gauge singlet thing, and we turn on a coupling lambda 0 for it. We can turn 2 additional couplings. Let me denote them by lambda 1 and lambda 2. And they couple to Q tilde to the third and Q tilde to the third. Okay? This seems like the same thing. Okay, I just take Q tilde and take it to the third power. And interestingly and non-intuitively, for G2, there are two independent singlets in the cubic. Like if you take a 27-dimensional representation to the third power, there are two different singlets that you can build. Okay? It doesn't matter if you wish, there are different ways to contract the G2 indices to construct the same singlets. It doesn't matter for us how that happens. We just need that this group theory fact that we have two different couplings that we can turn on. Finally, we have an additional coupling, so which I will denote by lambda 2ij, which we take this Q tilde and also this field Qi and Qj, and we symmetrized over these indices I and j. Okay, so there are many superpotential terms. Basically, there are 6 such terms because we have a symmetric representation of this SU3. This Qi, this index I is in a symmetric representation of SU3. So these are all the couplings we can turn on. Okay? These are the marginal couplings we can turn on, and some combinations of these marginal couplings together with the gauge coupling will be exactly marginal deformation. Okay, so remember that to understand which couplings are exactly marginal, the computation we need to perform is to collect all of these marginal coupling, to look on the set of these couplings. Let me denote it by lambda as we did. Yes? Exactly. Excellent. So we need to check that. I jumped on that step, and the reason I jumped off there about that step is because we're starting from a free theory. We're starting from a free Lagrangian. For a free Lagrangian, we assign R charges, which are 2/3 for all the fields. So if we look on the cubic interactions, all of them will have R charge 2. Okay? If we would have started from an interacting CFT and would try to deform it, we would need to perform this computation. But if we start with a gauge theory, like a free gauge theory, then we always start with free assignment of R charges. Okay? So these are marginal deformations of a free theory. When we compute deformations, we use the R charge of the fixed point. And the R charge of the fixed point here is 2/3. Okay, so we need to compute which one of these couplings are exactly marginal. We list all of these couplings. And then we compute a quotient with complexified global symmetry group. So the global symmetry group here is SU3 times U1. And let me write it here as SU3 times U1. But there is one thing that I don't write, and I will be a bit cavalier about it. Remember that we also have an anomalous symmetry. Okay, I mentioned that when one of these U1 symmetries, for example, the symmetry which assigns the same charge to Q and Q tilde is anomalous. If you will compute this anomaly, you will get something which is not 0. And you can think of this anomaly as something which shifts the gauge coupling. Okay? So what I will do, I will not write here the gauge coupling, and I will not quotient by the anomalous symmetry. Okay? Basically, their effect cancels each other. So they transform the superpotential couplings transform in the opposite way to the gauge couplings. So if I solve for this quotient, I can always solve for the quotient for the anomalous symmetry. Just a second, this is not true if we have multiple gauge groups. Then things will become more complicated. But here it is a true statement, and I will not get into doing that. Yes? No, if I find a U1 symmetry for which I have a 't Hooft anomaly, that just means that that thing that I thought is a symmetry is not a symmetry. That's it. Okay? That's the meaning of having these two. I want to gauge this group G2. If I build some U1 for which this anomaly is not 0, that just means that U1 is not a symmetry after I gauge this thing. Okay? So to perform this yes? With the anomaly?
Yes. No. I mean, the fact that
Right. So the way it goes, like this is a computation which needs to be performed, but the way it goes is that if you have, like if you have some, say, a single group, a single simple group that you gauge, you always can build an anomalous symmetry by assigning all the fermions the same charges. Okay, this assignment will be always anomalous. So, and there is always only one anomalous symmetry. You can choose the anomalous symmetry in a different way by mixing it with non-anomalous symmetry. But this symmetry is always anomalous. So if we do that, then all the superpotentials will have couplings which will transform under that symmetry with the same sign, like they will have the same charge, because all the fields have the same sign of the charge. Okay? So all the superpotentials will transform in the same way. So naively, if you just take the superpotential couplings, you will not be able to solve this quotient. It will be empty. But the gauge coupling transforms in an opposite way. Like if you compute how, if you do the transformation of the measure of the path integral, you shift the theta term, and you can do that computation, it always will transform the gauge coupling in the opposite way. Okay? So whatever you did, whatever the transformation you get from the superpotential couplings, you will be able always to cancel with some proper power of the gauge coupling. So that's the logic. That's a step I'm skipping because it's, well, I need to really compute how the gauge coupling transforms to show it for you. And it's important, here it is a simple fact that nevertheless needs to be shown. If you have many groups, this becomes more complicated because each group will come with an anomalous symmetry and you need to perform a honest computation to solve this quotient, which sometimes is not trivial. Yes?
So is it related to this fact that fermions measure change by the same factor of e to the power integral x square, so that adds to the theta term?
That's right. So that's how, like the proper thing to do, this is again something I skip, is to look on the complexified gauge couplings, which involves both G and Mills and theta, and then you look and you call this combination tau often, and then you look how tau is shifted under this anomalous transformation. So that's the meaning of saying that that anomalous symmetry shift the coupling.
This superpotential breaks this U1 symmetry.
Yes, that we will get to that. This superpotential, each one of these couplings breaks some of the symmetries, and that is the next thing that I will discuss. It will be important to compute this quotient. That's true. This symmetry, the symmetry SU3 times U1 of this free theory will be broken to something by these terms, and eventually we need to understand what will it be broken to, like what is the maximal breaking. That is the next thing I'm going to do. Okay, so to do this, to compute this quotient and to answer this question, I first need to understand what are the charges of different couplings. So to do that, we look on the charges of the various operators that are here, on the representations of them under the symmetry group, and then the couplings have the conjugate representation. Okay. So what are the charges? So what are the charges of these guys? So what is the charge of this Qi, Qj, Qk, epsilon I, Jk? This is the singlet of SU3, okay? I perform this baryonic contraction, so I get a singlet of SU3. So under SU3, this is a singlet, but it has some charge under the U1 symmetry. So what is the charge under the U1 symmetry? Each field has charge -3. So these guys have charge -9, okay? And if you wish, the lambda 0 has charge 9, and it is a singlet. I will work with the charges of the operators, not the couplings, but it's just a choice of convention. And then you can perform the same computation for each one of these couplings. So these guys are singlet of SU3 because these are not rotated by the SU3, and they have charge +3, both of them, okay? And this guy is the most complicated one. So it is in a symmetric representation of SU3. That's how I define it. I symmetrize these indices. And it has charge of -5. Okay, so there is a -3 coming from each one of these guys and +1 coming from these guys. So what I need to do now to solve for this scalar quotient, I need to find combinations of these representations which give me singlets of SU3 and U1. Okay, so that's a simple computation to perform. So let me perform it. So here it goes. So let me write to you a singlet combination of these couplings lambda 0, lambda 1, lambda 2, and lambda 2 ij. So two combinations are very simple. So if you take lambda 0, multiply it by lambda 1 cubed, this is a singlet. Okay? Under SU3, both of them are singlets. And the charges under the U1 are opposite, and one is thrice the other. So immediately you get this thing. Another thing which you immediately get is that lambda 0 times lambda 2 cubed also is a singlet. Just it's the same charges. Okay? So what this means that we immediately find that there are at least two exactly marginal directions. Okay? And the way it goes, the exactly marginal directions correspond to turning on the first superpotential term and one of the other two with some relative coefficient. And this power determines the relative coefficient. Like the coupling of one has to be thrice than another. But this is not important to us, so I'm not going into the details of exactly which couplings you turn on. It's just important that there are two exactly marginal deformations. And then the question, what symmetry is preserved when we turn on these two exactly marginal deformations? Yes?
What about couplings of the form lambda 0, lambda 1, lambda 2 squared?
We will get there. There are more couplings. I will get there, and I will get to more couplings, but at least, you know, I need to find singlets, and each singlet corresponds to exactly marginal deformation. So I find them one by one. There are two simple ones, and then we'll find the other ones. Okay? So we started with a symmetry which was SU3 times U1, which symmetry is preserved by, if I turn on lambda 0 and lambda 1, or lambda 0 and lambda 2 couplings. Which one? SU3, right? So the U1 is broken, but SU3 is preserved. Why U1 is broken? U1 is broken because these operators in the first line, they are charged under this U1. Okay? So there are two directions on conformal manifold that we already found on which U1 symmetry is broken, but SU3 symmetry is preserved. Okay? So now let us start exploring this conformal manifold, this two-dimensional conformal manifold. Once we start doing that, we shouldn't care about this U1 because it's already broken. Okay? This is a way to compute this quotient. Like you find some nice directions, then you go on these directions, you have less symmetry, then you have less of the quotient to perform. Okay? So, and then we need to find an additional deformation. So now we have these deformations that we turn on, and we are left with one coupling, this lambda 2 ij. Maybe 2 is a bit, okay, it has indices, so it's fine. Lambda 2 ij, okay? So now we need to build an invariant under this single coupling lambda 2 ij. In principle, it is charged under this U1, but remember that we already broken it after we started exploring conformal manifolds. So we only care about the representation under SU3. Okay? You can think of this lambda 2 as a 3x3 matrix, symmetric matrix of SU3. So there is an invariant that you can build, and it is just the determinant. Okay? This determinant of lambda 2 ij, if you compute the determinant, it is invariant of SU3. Okay? So in total, these are the only exactly marginal deformations we can find. We can, of course, mix them together. Like anything else that you will find will be some combination of these three invariants. Okay? The claim is that there are only three independent invariants. Of course, this times this is also invariant, and so on. Okay? And if you care about the U1, you will need to do something smarter, right? But again, the way we compute it, we go on this conformal manifold. On these two directions, we break the U1, and then we compute this quotient. So now an interesting question is, what symmetry does this guy preserve? Okay, it is naively, the couplings lambda are charged under SU3. And now you need to ask yourself, okay, I turn on these couplings. What symmetry do I preserve? Do I break the full SU3 or not? Okay, so this is a group theory question. So if you know your group theory well, you will think a little bit and you will understand that SU3 is broken, but not completely. It is broken to SU2. Okay? And this SU2 is such that this fundamental representation of SU3 here becomes a joint representation of SU2. So the breaking is like that you have a three-dimensional representation here, and it is broken, the group is broken, and this three-dimensional representation becomes a three-dimensional representation, but of a different group, of SU2. And let me give you a kind of a mnemonic, a very useful tool to understand how to check these claims at least. So we have these marginal deformations. They are in a six-dimensional representation of SU6. Okay? And we start with, of SU3. And we start with an SU3 group. What is the dimension of a joint representation of SU3? It's 8. So let's look on this guy. And if you remember the index computations, that's exactly what appeared in the index. There are marginal operators minus the conserved kernel. Now we assume here, I just impose it on you, that this group is broken to SU2. Okay, so let us decompose the six-dimensional representation of SU3 and the eight-dimensional representation of SU3 into representations of SU2. Okay? This is something which is easy to do. And the answer is that the six-dimensional, so this is an SU3 line, and here I write an SU2 line. So the six-dimensional representation of SU3 becomes a 5 plus a singlet of SU2. Okay, just perform your group theory. Okay, what the eight-dimensional representation becomes, what the adjoint becomes, well, there is it's a little bit trickier. So it is an adjoint of SU3 that we claim that decomposes into SU2. So we have to have the adjoint of SU2, and then we have to have something else, and the something else is a five-dimensional representation of SU2. And now see what happens. You look at this. This 5 is exactly the same as this, and it cancels out, and what you remain with is the singlet minus a 3. Okay? So what does the result mean? The result means that you have a single singlet. Okay? You remain with a single singlet, but with a group which is SU2. Okay? If you would not have gotten a singlet in this computation, that means that you did something wrong. There is no singlet when you have a six-dimensional representation of SU3. And the same thing, like if you would gotten more characters with a negative sign, that would mean that you identified the preserved symmetry incorrectly. Okay, this is some mnemonic rule that I will use now and then. Okay, so that's a consistency check that, you know, this statement that SU3 is broken to SU2 is correct. Right, so this is, at this level, I just tell you a trick how to understand what symmetry is preserved. You take the marginal operators, okay, that you want to turn on, some combination of them, and these operators transform in a six-dimensional representation of the group SU3. So you put with a minus sign the joint representation of your symmetry you start with, and 6, the things from which you want to build your Keller quotient. That's what it represents. Okay, and there is a physics understanding of that. Remember that I told you that what appears, for example, when you compute the index in certain order, there appear marginal operators with plus sign and conserved currents with a minus sign. Exactly this combination. And then what I told you also that there is this theorem that marginal operators can be either exactly marginal or marginally irrelevant. So a deep meaning of that statement is as follows, and that I didn't mention, so I will mention it now. So if you have a marginal operator, the only way for it not be exactly marginal is if it eats a conserved current, like in Higgs mechanism. Okay, so you really can show that. So the only way you have a marginal operator, but it is irrelevant, is if it somehow can be coupled with a conserved current. And that is exactly what this computation shows you. Some of the conserved currents disappear, and some of the marginal operators disappear, but they cancel each other. Okay? And then you are left with the singlet and the symmetry that you preserve. Okay? If you don't like this mnemonic, just take it as a statement or compute it in a different way that you like. Okay? Understand if you have a determinant, why SU3 is not completely broken, but only SU2 remains. So then we have the following statement. The statement that we have, so we computed this quotient, and we can write the following thing. We can write that the dimension of the conformal manifold is what? It's 3, right? We found 3 exactly marginal deformations, and that the symmetry preserved on the conformal manifold, this GF that I have written down, is equal to what? SU2. Okay, so we have a conformal manifold which is 3-dimensional, but the symmetry on this conformal manifold is not completely broken. It's broken. We start from SU3 times U1, but we have SU2 remaining. Okay. Now another thing we need to do, or we can do, we can compute some 't Hooft anomalies of this SU2. Okay, they are also invariants. So one interesting anomaly that we have here is trace R SU2 squared. Okay, how do I compute this anomaly? Again, we look on this theory, and then we look what is it built from. We have this field in the 27-dimensional representation. Is it charged under SU2? No, it's a single field. It is not charged under SU2. We have these fields which are charged under SU2. In which representation are they under SU2? In the adjoint representation, okay? And how many fields in the adjoint representation are there? This is 7, excellent, okay? Because we have 3 times 7, where 7 is the fundamental of G2. So if we think of this group, there are 7 fields in the adjoint representation of SU2. So I just continue the computation of that anomaly here. So we have an adjoint of SU2, like the trace SU2 square in the adjoint representation gives us a 2. Then we have the contribution of the R charge. It's trace R SU2 square. So it's 2/3 minus 1. And we have times 7. So what this anomaly is, you compute it and you find that it is equal to minus 14/3. Okay? So we know what the dimension of conformal manifold is, we know what the group is, and we know what the 't Hooft anomaly is. You can also compute any index you want. I will quote the index later, but in principle, we have discussed how to compute indices of gauge theories. You can just compute them. Okay, is this clear? So this is all the information just that we derived about this theory T1. Okay, and now we turn to the fun part of the computation. That's right. Exactly, excellent, exactly. So there are 2 directions on the conformal manifold, which preserve a bigger symmetry as SU3. So the conformal manifold has this structure. So we have some plane on which we have SU3. And then in the bulk, like in the 3rd direction, we have only SU2. So on a generic locus, we have an SU2 preserved. And then on some plane, we have an SU3 preserved. Maybe if you go to strong coupling, this is this free G2 gauge theory. So you start going from it, you have an SU3 symmetry in the plane, and then SU2 symmetry on a generic locus. Maybe if you go somewhere else on the conformal manifold, there are emergent symmetries far away. But at least in the vicinity, that's what we see. There is a bigger symmetry. Yes, you also get a U1, but that is a free point. I think we discussed it in a discussion session at some point, that it is some very, like the free point is a very, very singular point, so we will typically not discuss it. Okay, so now that we have information about our theory T1, we want to find theory T2. So what should we do? Okay, so here is all the invariant information that we have. We have NV equals 14, N chi equals 48, and we know some information about the conformal manifold. So I want to ask, what can be the theory T2? So what do I do? Well, I can find A and C, but I find A and C to find NV and Nchi. So this is like if I'm giving you a theory abstractly with A and C, okay, then you translate them into NV and Nchi. But here, I already gave you the NV and Nchi. So you already know how many vectors and how many chirals it has to have. Like if there are two Lagrangians on this conformal manifold, another way to phrase what I'm saying is if there are two different Lagrangians, both of them have to have the same number of vectors and the same number of chirals. Again, because they have to solve the same equation. The A and C doesn't change, so they will have the same solution for NV and Nchi. So I'm looking for another solution of T2, but that T2 has to have still 14 vectors and 48 chirals. Okay, so now I need to look for a gauge theory which has 14 vectors for the beginning. Okay, so one such gauge theory is G2. We started with, we found something. You can look for other G2 theories, which are conformal, but you can list them. But the other theories which have G2 gauge symmetry don't have 48 chirals. Okay, you can build other G2 conformal theories, but they have different number of chiral fields. So we need to look for something else. So let me make a very short list of gauge groups that we can consider. So here is a gauge group, and here is a dimension of the gauge group. So we'll go from smallest, and we will enlarge. So the smallest thing we can consider is SU2. We don't consider U1 because U1 gauge theories in 4 dimensions are always infrared free. Okay, so they are not interesting. So we have an SU2, then we have an SU3, then we have a USP4, then we have a G2, and we can continue. And I order the things according to their dimension. So dimension of SU2 is 3, of SU3 is 8, of USP4 is 10, of G2 is 14. Okay? So what I need to do now, I need to build these 14 vectors from these numbers. Okay, these are not arbitrary numbers. So there are not too many ways to build 14 out of them. So I need to write this equation. 14 equals sum over some groups and their dimensions. Of course, the dimensions are positive, so I have not too many options. So what is the solution to this? First of all, there might be no solution to this equation. Okay, if there is no solution, again, there is no other theory T2. But in this case, there is a solution. Okay, magically, 14 is 3 plus 3 plus 8. Okay, so let us do this computation. Okay, this is equal to 14. Okay, so since this is equal to 14, we now can try to look for a gauge theory which has 2 factors of SU2 and 1 factor of SU3. Okay, so let me do it here. Okay, so the dual theory that we are looking for, let me denote it here by this T2. It has to have an SU3, 2 factors of SU2, and 1 factor of SU3. Okay? If a gauge theory dual exists, which is different from G2, this has to be the gauge group. There is no other choice. This might not work, but if something exists, this is the only choice. Now, what we did, we matched the number of vectors. The number of vectors is 14. We also have a number of chirals we need to match. So now what we start doing, we start adding matter to this theory in such a way that the total number of fields will be 48. So of course, there are many ways to do so. So here, but again, many ways, but not infinite number of ways. So you can do it on a computer, or if, like in this case, if you're a little bit used to such computation, it's immediate. So I will give you the answer. So you can add 3 bifundamental fields here. And then what you do is the following. You also add bifundamental fields like that, and bifundamental fields like that. And you add 2 fields that I will denote by these dotted lines. Here, let me call this field X. This field I will call X bar. This will be phi. This will be phi tilde. And this will be Q. So these x's are, one of them is in a 6-dimensional representation of SU3. Another is in the conjugate representation, which is 6 bar. Okay? You can count the number of fields that I have added here. So there is 6 plus 6, which is 12. There is 6, like 2 times 2 times 3, which is another 12. There is another 12 coming from here. And there is 3 times 4 coming from here. So in total, we have 48 fields that we add. Okay? You can do other things. For example, you can change the arrows here. One will be fundamental, another will be anti-fundamental. It will still give you 48 fields. And you can do other, you can try to find other theories with a number of vectors which is equal to 14 and number of chirals which is equal to 48. Okay, it's a nice game to play. The point is that this theory is special. Okay, so first of all, when you do this computation, after you are done, you now need to repeat the computation that we did for theory T1 for this theory. We need to find that the conformal manifold of this theory, the dimension of the conformal manifold, the number, the symmetry which is preserved on the generic locus of this conformal manifold, and if something is preserved, the various 't Hooft anomalies. And if these things work, we will also need to check the index. So you can do, consider other theories, but the claim is that these things will not work. Okay? And for this thing, we get exactly the same result. Okay? So let me outline how it works. Okay. Now this computation is a little bit more involved because there are 3 gauge groups. Okay, so it's just, you need to repeat the same computation, but it's just lengthier. Okay, but it's not much more complicated. So first of all, let me ask the following question. Is this, are the beta functions of each one of these gauge groups marginal? Okay, so how many fundamental fields each one of these SU2s sees? Okay, so there are 6 coming from here and 6 coming from here. Okay, so there are in total 12 fundamental fields that in this language that we used last time of dividing always to fundamentals and anti-fundamentals, for SU2 they are the same, but let's still think of this, say, as fundamentals, as these anti-fundamentals. This is SU2 with an F equals 6. 6 is 3 times 2, right? And we already have shown last time that if we have an SUN theory with 3n flavors, the beta function vanishes, okay? So immediately we know that these couplings, the couplings of these 2 SU2s are marginal. Okay? Then you need to compute the beta function of this guy. Please do so, okay? And verify that with this matter content, the beta function will be 0. Okay? You will have contribution from fundamentals, from 4 fundamentals, from 4 anti-fundamentals, from a field in a 6-dimensional representation and 6 bar, and the contribution of trace R SU3 squared, this computation has to give 0. Okay, and that gives 0. Now, let us analyze the various symmetries and couplings of this theory. Again, I will not do it in the full detail, but it's exactly the same computation as we did for the G2, but longer. Okay, so just let us see what the symmetries are. So what are the symmetries of this theory? Okay, what do you think of the free theory? Exactly. So what we can rotate the 3 Qs. This gives us an SU3. We can rotate the phi's. This gives us an SU2. We can rotate the phi tildes. This gives us another SU2. And also we have a bunch of U1s. We have a lot of U1s here. Okay, so let me even not write how many. There are some U1s here. What I want to stress that this symmetry of this theory, and when a theory has more than one gauge node, typically called a quiver theory. So this quiver theory has a lot of symmetry, and it is different than the symmetry that we had for the G2 theory. But this is the symmetry of a free theory. Okay? Once we will go out of this free theory on the conformal manifold, most of this symmetry will be broken. Okay? What are the marginal operators that we can have here? Okay. Again, we need to build gauge invariant operators, which are cubic in the fields. Okay. So let me give you examples of things that you can build. So for example, you can take phi, multiply by phi tilde. This is fundamental, anti-fundamental, so it's singlet under this SU3. And then we can multiply by q. So an example of an operator is phi tilde times q. Okay. Under, how is it charged under these symmetries? This operator. Okay. We have two choices for phi. We have two choices for phi tilde, and we have three choices for q. So if I write it in representation of SU3, SU2, and SU2, this is in some horrendous representation. It transforms under all the SU2s and the SU3, and it also has charges under U1s. Okay. We can have other marginal operators. For example, x cubed is a singlet. X tilde cubed is a singlet. Phi squared x is a singlet. Phi tilde squared x tilde is a singlet. Okay. So we have a lot of marginal operators. We have a lot of couplings. Again, this looks different than the G2. The number of marginal operators is different. Each one of them comes with a coupling. Okay, so let me just collectively call the couplings that you will obtain here by lambda prime. So in order to understand the conformal manifold of this theory, I need to list all of these couplings and quotient by the complexified global symmetry group of this theory, which is SU3 times SU2 squared times a collection of U1s. Okay? So it's a different computation that we had before. It's not the same computation because the starting point is different. The point is that if you perform this computation, you arrive at exactly the same result. Again, it's a lengthier computation, so I will not perform it explicitly, but you will get that dimension of conformal manifold is 3. The symmetry which is preserved on general locus of the conformal manifold is SU2. So let me just tell you what is this SU2. What do you think this SU2 will be? Just a guess. Find the natural SU2. Okay, we have an SU2, an SU2, and SU3. So what will be preserved is some diagonal combination of all of them. So diagonal combination of these two SU2s, when you lock rotations of this with rotations of that, and when you embed an SU2 inside this SU3 in the same way as we did before. So this fundamental representation of SU3 becomes an adjoint of SU2. Okay, so that is the SU2 which is preserved. Okay, again, this is a computation that you need to perform. It's not, I don't expect you to see it immediately. Okay, but one computation let me perform on the blackboard is the 't Hooft anomaly of this SU2. Okay, so look on trace R, this SU2 squared. Okay, this anomaly has to match this anomaly, but the computation is different. Okay, it's completely different theory. So again, let us see how it works. Okay, where do I have this computation? Here it is. Okay, so first of all, let us look on these fields Q. They transform under a joint representation of this SU2, the diagonal SU2, the SU2 under which these are fundamentals, and this is the joint. So the fields Q will contribute 2, which is just trace SU2 squared in a joint representation. Then we have 2/3 minus 1 times what? How many such fields are there? 3 is the joint representation, but there are 4 of them. Okay, so there are 4 fields in a joint representation. This is contribution of the Q's. Then we have the contribution of the phi and the phi tilde. They are in the fundamental representation. So we have a half times 2/3 minus 1, which is the R symmetry. And then how many such fundamentals we have? Okay, so we have 6 coming from phi and also 6 coming from phi tilde. So in total, we have 6 times 2, 12. Perform this simple algebraic computation, and you will obtain that this is equal to minus 14/3. Okay, it's a completely different computation, but which gives the same result. Okay, so the dimension matches, the group matches, the anomaly matches. You can compute the index, and it also matches. Okay, let me just maybe write it. So the index will look like that. If you compute the index in both theories, where you turn on only parameters for the symmetry which is preserved on the conformal manifold, only for this SU2, the index will look like the following thing. It will start with 1, then will be PQ to the power 2/3, and then you will have a singlet of SU2, another singlet of SU2, a field, something which transforms in the 5-dimensional representation. And then you will have something which looks like that. Maybe somebody can tell me what I should write here. What is the contribution which multiplies PQ? Marginals minus the currents. So on the generic locus of conformal manifold, we lost all the marginals. We are left only with exactly marginals, right? So the number of exactly marginals is 3. Okay, and there are singlets under the SU2 global symmetry, which is preserved, because if we go on them, we don't break further the global symmetry, but then we have to have minus the conserved currents, and we will have a -3. But this 3 is the number 3, and this 3 is the character of the joint representation of SU2. And then we have other things. Then you can continue computing. So both of these theories, this quiver theory and G2 gauge theory, give exactly the same result. Okay? So we can conjecture that these two theories are conformally dual to each other, that they sit on the same conformal manifold. This is something it would be very hard to guess, okay? But it is, you see, it is derived extremely linearly, very algorithmically. Okay? So maybe you are not interested in G2 theories with weird matter, okay? So we will need to apply this algorithm in some more fruitful setting. Okay, but I think this is the simplest example, which is non-trivial, where you can see something interesting happening. Yes?
Can one say anything about which of these theories could be strongly coupled and like how it works, strongly coupled on one side, also strongly coupled on the other side?
Right, so let me comment on this. So what we can say is like that. Again, we have a 3-dimensional conformal manifold, so there is some 3-dimensional space. At some point, we have this G2 theory, okay? At this point, this G2 is weakly coupled. We have no idea what is the coupling for the quiver theory. All we know is that there is some other point, or we conjecture. We don't know it, we conjecture. All the computations are consistent with the statement that somewhere else on this conformal manifold, there is this weird quiver. There, this guy is weakly coupled. What is the coupling of this guy? I don't know, okay? These types of computations going across, basically we go here across wall of strong coupling. The wall of strong coupling is somewhere between these two theories. It's not an RG flow wall, but it's this, we just tune continuously the coupling to be strong. We don't know how, what is the map. For example, in n = 4, we know that tau goes to -1/tau. We know that there is some very nice map. Here we don't know that map. Okay, that's actually an interesting open problem. Like in these types of dualities, is there a nice map between couplings? And remember that there are 3 directions that you can go. So for n = 4, if you preserve n = 4, there is only one complex direction. So the map is very simple. The guess would be that there has to be that this theory is really in some strongly coupled regime of this theory and vice versa. But what is exactly the map? You should discover. Okay? So this is an example how to apply this algorithm, and now I will give you a little bit details on another example, and then we will dive into geometry. Okay? So let me do this other example. So in this other example, it will be an abstract example. So what I will tell you, just some abstract information about theory T1. So I claim that there is a theory T1 with the following information. There is A and C anomalies, which are equal to 15/4 and 9/2. Okay, so A is 15 over 4 and C is 9 over 2. This is the first piece of information I give you. The second piece of information is that it has 66 relevant operators. And these relevant operators have R charge 4/3. Okay. Another piece of information I give you that this theory has 74 exactly marginal deformation. So a huge conformal manifold, which is 74-dimensional. And finally, that the symmetry preserved on the general locus of the conformal manifold is nothing. Okay, there is no symmetry. And I ask you to compute, to find the Lagrangian dual for this theory. Okay? It has a large conformal manifold. And the question is whether it has a Lagrangian description. So it is not just a cooked-up theory. It's a very well-known and very well-studied theory. It is known, it has a name. It is called R04. Okay? And it is obtained by taking some 6-dimensional theory, a 2,0 theory, and compactifying it on some surface. And this R04 theory has n equal 2 supersymmetry. Okay? And in addition, when you get this n equal 2 theory, it has a lot of exactly marginal deformations. And when you go on these exactly marginal directions, the n equal 2 supersymmetry is broken to n equal 1. I didn't talk about n equal 2 supersymmetry in these lectures, but it's just having more supersymmetry, a more symmetric case. Okay? So there is this abstract theory. Usually these types of theories are called non-Lagrangian. You cannot write, you can try to write an n equal 2 Lagrangian for this theory and you will fail. You cannot write an n equal 2 Lagrangian. But you can apply this type of a technology to try and derive an n equal 1 Lagrangian for it. It has a huge conformal manifold. Okay? So you just apply the technology. So I will just start applying the technology and then we will quote the results. Okay, so to apply the technology here, we need to translate first these anomalies into numbers of vectors and chirals. So for that, I remind you what are these A chi and C chi, okay, that we have written down in the previous times. So the A anomaly of the chiral field and the C anomaly of the chiral field are equal to 1 over 48 and 1 over 24. And A, V, and CV are equal to 3 over 16 and 1 over 8. Okay, so you use these numbers and use these anomalies A and C to derive the number of vectors and number of chirals that this theory has. Okay, again, this is solving a system of 2 linear equations in 2 variables. It's not too hard to do. And what you will find is that NV equals 12 and N chi equals 72. Okay, so this is the starting point. First thing, these numbers are integer. Okay. Here, it was not obvious that the numbers are integer. In the previous case, we started with the gauge theory. We started with NV and N chi, which are integer. So, you know, the other solution should have been the same. So it was trivial. But here, I give you some anomaly, so it's not clear at all that these numbers will turn out to be integer. But they turn out to be integer. So now we need to look for a gauge theory which has 12 vectors. Okay, what is that gauge theory? Okay, there is a unique solution. Look at the table of the groups. So again, we need to solve the equation. Sum over dimensions of groups is equal now to 12, not to 14. So how do you solve that? It's 4 SU2s. Okay, that's it. So we will have a gauge theory which has 4 SU2s. There is no other choice. Okay? And now we have 72 chiral fields, so we need to find matter content which will have 72 chiral superfields. Okay? A choice which works, again, there is a finite number of options, but a choice that works is the following very symmetric quiver theory. What does it mean? We have a bifundamental field between each pair of SU2s, and each SU2 also has additional 6 fundamental fields. Count the number of fields that are here, and you will find that that number is 72. Also, look at on every SU2, how many fundamental chiral fields it has, every one of these SU2s. It's 12, okay? So 12 is, again, an F equals 6, which is, if we think of this SU2 as SU1, an F equals 3. So beta function of which each one of these SU2s is marginal, okay? So now what we need to do, we need to, again, to analyze the Keller quotient, write all the marginal operators, and quotient by the symmetries. What are the symmetries here? There are 1, 2, 3, 4 SU6 symmetries. There are a lot of U1 symmetries. Okay, so there is a lot of symmetry. There are a lot of marginal operators. So what are the marginal operators? Again, we need to build gauge invariants from cubic combinations of the chiral fields. So just to give an example, what are they? For example, we can take this field, and this field. This is one option. This field, and this field, and so on. We can look on these triangles. They're also, like, if we go on these triangles, we take this field times this field is also gauge invariant combination. So there are a lot of gauge invariant combinations that we can write. There are a lot of marginal operators. There is a lot of symmetry. You perform this Keller quotient, and you find that you have a 74-dimensional conformal manifold on which all the symmetry is broken. It didn't have to be so. We could have found a theory with this matter content, but the number of exactly marginal operators would be different, or the number of, or the symmetry on the conformal manifold would be different. That's not what we find. We find exactly this number. Moreover, if you compute the relevant operators, you again find exactly 66 relevant operators, and I encourage you to do so. Okay, what are, just to get started, what are the exactly marginal, the relevant operators? It's easier to count. So the relevant operators that you will find will be quadratic combinations of fields. Okay, let me call this field Q, for example. So how you build a gauge invariant operator from Q, which is relevant? QQ, take a Q squared. To build a singlet of this SU2, you need to anti-symmetrize the gauge indices. So you will need to anti-symmetrize also these indices. Okay, so how many such operators you will get? So you anti-symmetrize this, you will get 15 operators like that. So you will get 15 operators from here, 15 from here, 15 from here, 15 from here. Total is 60. There are 6 more that you can find. Where do you find them? Exactly. The bifundamentals, there are 6 of them, and you can, let me call this Q, so you can take Q squared. Okay, you anti-symmetrize both gauge indices. It is gauge invariant, so in total you have 66 relevant operators. Exactly what you need to match to this thing. Okay? So here is an example of a non-Lagrangian theory with n equal to supersymmetry, which has a Lagrangian description as an interesting quiver theory. Okay? This quiver theory has only n equal 1 supersymmetry. It has a huge conformal manifold. So again, the picture is some version of the picture up there. Let me use the same picture. So now we have a huge conformal manifold. Okay, let me write it abstractly like that. This is the conformal manifold. At some point of this conformal manifold, we have this theory R04, which has n equals 2 supersymmetry. Then we start exploring this conformal manifold, and the conjecture is that somewhere on that conformal manifold, this is a weakly coupled description, completely Lagrangian, or vice versa. Start from that, go to strong coupling in some way that we don't know what the value of the coupling is, but eventually you will hit this theory R04. Again, this is a conjecture which can be checked in many, many different ways. Yes?
Is there a way to say that there are other possible Lagrangian theories dual to the starting one, which are connected by marginal?
Yes. So you need so what you need to do, you write all the possible Lagrangians. Like the number of possible Lagrangians is finite. Go over all of them. Okay. And sometimes, and we will see an example today, there are more than one. Sometimes there are many. Okay? In this case, you know that the gauge group has to be this. Okay? There is no other way to build 12 from dimensions of simple groups. But the matter, you might say, maybe I can find another matter assignment, like another way to add matter. In this case, I don't think there are, but you know, maybe when we did that, we missed some possibility. Okay, well, all we know is that this works. We checked other things, but maybe we missed something. Okay? I don't think we did because it's very simple, but that's the idea. You go over this finite list and look for all the possibilities. Yes?
Based on number of vectors, should we have SU3 times SU2 times U1?
No, because U1 will go to a free theory. It will not be like conformal in the usual sense. Like you will have weakly coupled vector fields. Okay? And for example, one thing that you know about this theory is that it doesn't have a weakly coupled vector field. Like if it has weakly coupled vector field somewhere, like you are talking about infrared, right? So it will have weakly coupled vector fields everywhere. And we know, like that's, if you wish, a piece of information. When I say like interacting CFT, I'm saying that there are no weakly coupled vector fields. Okay, so we never look at U1s. Yes?
So the gauge theory, we know that n equals to 1 supersymmetric. So even if we compute the one loop beta function to be 0, how do we know it's exactly marginal?
That's the magic of that computation, of this scalar quotient. That's a very good question. So that's a very, very valid question. It's completely non-trivial, but the answer is there. Okay, that's how you derive this technology. I cannot explain it quickly, but well, remember this, that there is a simpler way to explain this, which doesn't give you exactly that, but it is this older result by Lee and Strassler in a very beautiful paper. What we discussed at some point is this non-renormalization of superpotential, where we said that the beta function of superpotential couplings is a linear combination of anomalous dimensions. So for each superpotential term, we can write some kind of a linear equation like that. The beta function, say, of the coupling lambda I is a linear combination of anomalous dimensions of various fields that appear there. So there is such collection of equations. For gauge couplings, there is a similar equation that you can write. It is called the NSVZ beta function. Okay? It's also like the beta function for a gauge field is given as a linear combination of anomalous dimensions of fields which transform under the gauge symmetry. Okay, now we want to find a conformal theory. So we just set all the beta functions to 1. So now we have a set of equations in anomalous dimensions, and the anomalous dimensions themselves depend on all the couplings. Okay, so the basic idea is that if the number of equations is smaller than the number of parameters of couplings, like number of independent equations is smaller than the number of parameters, you will typically find solutions, no matter how complicated this depending on the coupling is. Okay? This is the Lee and Strassler argument. It doesn't give you directly this thing, but this is a kind of a more sophisticated way to rephrase that argument. Okay? It looks completely different when phrased like that. Okay. So let me now turn to the more interesting application of all of this story. So we looked at the Lagrangian that we found, the dual Lagrangian that we found for a Lagrangian theory. Within a Lagrangian dual, though I didn't give you much details for a theory, you abstractly define. And I mentioned that the way you define this theory is by taking some 6-dimensional theory, which is strongly coupled. You compactify it on some surface, and you can predict that certain 4-dimensional quantum field theory exists, and you predict that it has these properties. And then we looked for a dual of that theory. So what we want to now discuss is how to systematically, or let's say at least more systematically, address these questions of starting from a higher dimensional theory, and we will start from a 6-dimensional theory, compactifying it on a general surface, predicting that there exists some four-dimensional theories, computing their various properties, and finding dual to these theories. And by doing so, we will discover a lot of interesting phenomena. We will discover a lot of dualities. We will see how a lot of dualities that we have already seen arise in this context. In particular, the aim will be to see how the theory with the 6 emergent symmetry that we discussed last time emerges from this computation, and how Seiberg dualities that we have discussed emerge in this setup. So let me start by saying several words about 6D. Okay? So we will not discuss 6D physics at all. Okay? In these lectures, I focus completely on 4D physics. So the only physical properties I want to discuss are properties in 4 dimensions. So we will use 6D as an input to our computation. So the main thing that you need to know is that 6D CFTs exist. Okay? It's a highly non-trivial statement. Again, if you try to write Lagrangians for 6D CFTs, all of these Lagrangians are free. Okay, they flow to free theories. So none of them will give you a 6D interacting CFT. Okay, to build interacting CFTs, you need to go to some more sophisticated techniques in string theory, brane construction, SEM theory, F theory, and we don't want to go there in these lectures. Okay? So point number 1, these CFTs exist. Then what we know about these 6D CFTs is that they are intrinsically strongly coupled. Okay? We cannot easily compute about them anything. However, we can compute a lot of bounds for them. Okay? Again, using sophisticated string theory techniques, very similar techniques to what we have discussed for 4 dimensions. So various types of anomalies. Okay? Some things which, you can deform these theories to go to some weakly coupled gauge theories after deformation, compute something for these weakly coupled gauge theories, and then deduce something about your starting point. So basically, the idea is a little bit opposite from what we were discussing. So you start with this 6D strongly coupled CFT, you do to it something, and then you get some weakly coupled Lagrangian. Okay, something which looks boring. Okay, but some information that you can compute here. So here is our wall of strong coupling. Some information that you can compute here actually tells you something about your starting point. Okay? So you need to develop all of this technology in 6 dimensions. And typically, it's not just field theoretic technology, it also involves stringy technology. But that's important to know that you can predict various bounds of these 6-dimensional theories. Okay? There are anomalies, there are global symmetries, and so on. Okay? And we will use that information as an input to what we are going to do. Another thing which is important, that will become important eventually, is that if you take these 6D theories, at least some of them, and deform them in some way in the following sense, so you take a 6D CFT, which is supersymmetric, you deform it by placing it on a circle. Okay? You take a 6-dimensional theory, you place it on a circle, and maybe in addition to placing it on a circle, you turn on some background gauge field for the 6D global symmetry. Okay? This is a strongly coupled theory. You don't know much about it. You deformed it in some way. So there is strong coupling thing happening, actually starting from your starting point. There is something happening. Then you get some quantum field theory. What is this quantum field theory? In how many dimensions it is when you go to infrared? So you get a 5-dimensional quantum field theories. So for some choices of 6D theories, some choices of these deformations, these quantum field theories have a Lagrangian. Okay? Not for all 6D theories and not for all deformations. Sometimes they still are strongly coupled, you don't know much about them. But in some cases, again, using brainology and various techniques, you can derive that. You have an effective theory, which is a 5-dimensional quantum field theory, Lagrangian theory. Lagrangian theories in 5 dimensions are infrared free. So the way you think about this quantum field theory is again, as something which is UV completed by your 6D starting point. So this is an effective low energy description, which is UV completed by 6D theory. And a lot of this information is known, like what are these theories, 6D theories, and what are the compactifications which lead to gauge theories. Okay? Sometimes such theories are called KK theories, if you will hear this name. Okay? Some kind, you reduce on a circle, and somehow the KK mode, like you from the KK modes that you see, you can reconstruct everything. Okay? But again, it's not that trivial to reconstruct that 6D theory. You just know the low energy description, and it is UV completed in 6D, but many times by studying this field theory, you can deduce some of the bones of the 6D theory, again, by the same logic. Oh, no. So there are two possibilities that can happen. So you can have a 5D QFT. You can find a 5D Lagrangian. There can be actually three possibilities. So I give you a 5D Lagrangian. Then it is an IR-free theory. You cannot write something which is UV-free. But then there are several possibilities. One possibility that it is some effective description of a deformation of a 5D CFT. That can happen, and that happens. It can be that it is an effective description of a compactification of the 6D theory. That's what I'm discussing here. And it might be that this theory doesn't make sense, like it doesn't have a UV completion. That also can happen. Okay? So here, since we are starting from 6D, we are considering this scenario, that we get a 5D theory which is UV completed in 6D. Okay? So now, given this information that we can derive, and again, as I have given you here this type of information, I will give you some information following from this type of logic, but I will just throw it on you. Okay? To derive it, it takes a lot of time, and simply defining, for example, what F theory is and things like that. We don't need that. We just need that information to do some discussion in 4 dimensions. So what will be a question we will want to understand? So the question was posed already in the first lecture, and it will be of the following type. We will start from 6D with some CFT. Okay? And we will place that 6D CFT on a 2-dimensional surface, on a Riemann surface. Okay? And maybe we will turn on also background gauge fields. Okay? We will discuss that. And again, this is a strongly coupled theory. When you place it on a 2-dimensional surface, you flow to something in 4 dimensions and to some QFT in 4 dimensions. Okay? And in general, you will be able to deduce some of the information about this 4D theory by, again, following these various anomalies, indices, and so on. And we will take it as prediction. So here is the strong coupling region, and you will be able to predict some properties of this QFT. Okay, what we will be interested in is in understanding this 4D theory. In particular, we will ask a question whether there is a direct description of this theory in 4 dimensions. So there is one definition of this theory in this as this compactification. Let me denote this theory by T6D, and this theory I will denote by T4D. Okay, which depends on my choice of the 6-dimensional theory and the choice of this geometrical data, okay, on the compactification surface and maybe some background gauge fields. Okay? So given a 6-dimensional theory and geometry, we produce a 4-dimensional theory. There is this abstract definition of the theory. We don't know much about this theory except for the bones, following from the general logic. But what we will want to discover is whether this theory has a Lagrangian description directly in 4 dimensions. And we will want to understand systematically such Lagrangian descriptions, say for a given choice of 6D theory and any compactification, or for some choices of compactification for any 6D theory. Of course, ultimately, maybe we will want to understand these 4D theories for any 6D theory and any compactification. We are not there yet. So in this, like in what remains, like in the next 2 lectures, I will in detail discuss a construction for a very particular 6D theory, and we will derive compactifications on any surface. Okay? And then we will see how all this random information that I talked about, except for the G2 theory. The G2 theory is weird. I don't know how to obtain it in this type of setup, but many of the random facts that I discussed about 4D will emerge very naturally, geometrically from this type of compactifications. Okay, so let me make another kind of a diagram of what we are doing to stress what is the story, and then we will start discussing the concrete computation. Okay, so the story is like that again. Let me draw it a little bit differently, but I think it gives an idea. So we start from 6D with some CFT. Again, it's just a different way to draw the same picture. Then we go to low energy. So we go to some 4-dimensional theory. We place the 6D theory on some geometry, maybe with gauge fields. And then this compactification leads to a theory which might have a conformal manifold of the type that we have discussed. So it will be a CFT which lives on a conformal manifold. That conformal manifold might be a point. Okay, there might be no exactly marginal deformations, but in general, you will expect a conformal manifold for reasons that I will mention. And what we want to find, we want to find a Lagrangian in 4 dimensions, which will either flow to the exactly same conformal manifold, so it will be a theory which flows, or it will directly describe this conformal manifold, like it will be a conformal theory. Okay? So in a sense, what the Seiberg dualities that we have discussed last time, they're infrared dualities where we start from 2 different theories in the same number of dimensions. Okay? We started from 2 theories, theory 1 and theory 2, in 4 dimensions, and we have flown to the same theory, or more generically, you can consider flowing to the same conformal manifold. But what we have here is the duality across dimensions. So let me call what we are looking after is a cross-dimensional duality. When we have a theory in 1 number of dimensions, in 6 dimensions, another theory in 4 dimensions, but they really flow to the same quantum field theory in the infrared. Okay. This quantum field theory that is here might be UV complete by itself. It might be conformal, as I mentioned, or it might be an effective theory, like that 5D story. It might be that it is an effective 4D description, which is only UV completed in 6 dimensions. So there are a variety of possibilities. The latter possibility we will not encounter in these lectures, but it is a possibility. Okay, so that's what we are after. Any questions? Okay, so I have time to start the concrete discussion. Very good. Okay, so the example that I will consider is very concrete. Okay. Write it here. So our starting point is in 6 dimensions. I will take some 6D theory, one of the simplest interesting 6-dimensional theories that exist there. And we will try to build this dictionary between compactifications of a 6-dimensional theory and 4-dimensional theories. So the theory that we will start with in 6 dimensions is called the E-string theory. Okay. All you need to know that it is some theory, some CFT in 6 dimensions that exist. It has a symmetry in 6 dimensions that will be important for us. And that symmetry is E8. Okay. Again, this funny symmetry, the largest exceptional group, E8. You know a lot of things about this theory. For example, you know anomalies of this theory. Okay. You know what are all of the anomalies of this theory. You know some of the operators of this theory. Another thing you know is if you take this 6D theory and you put it on a circle with some choice of background vector fields, you get in 5 dimensions an SU2 gauge theory, okay, with 8 fundamental fields. 8 fundamental fields. And when I say that, I need to tell you what are exactly the fundamental fields and what are the gauge fields. So this theory in 6 dimensions is a supersymmetric gauge theory. You compactify it, you get some supersymmetric gauge theory in 5 dimensions, but the supersymmetry that you get in 5 dimensions is not the same supersymmetry that we discussed in 4 dimensions. So we need, in principle, to analyze the supersymmetry in 5 dimensions. So the fields that you get here in 5 dimensions are called hypermultiplets. They are similar to hypermultiplets in 4 dimensions for n equal to supersymmetry for the people who know that. So that's what I mean here by fields, but again, the details of that are not going to be critical for us. Again, and the meaning of this theory is like that. It is an effective theory in 4 dimensions. It is not UV complete in, sorry, in 5 dimensions. It is not UV complete in 5 dimensions. The way to think about it is that it is UV completed by the 6-dimensional theory on a circle. Okay? Yeah, this is a fact that we will need to know. Another fact that we will need to know, and this is a quantitative fact that we will use, is that if you take this E-string theory, compactify it on a genus G surface, okay, we take this theory, and we place it on a genus G surface, okay, genus G, with no background gauge fields. And by background gauge fields, to be more concrete, let me define what I mean. So this theory has a global symmetry. Okay? It's an E8 symmetry. It's a rank 8 symmetry. So I can look on various Cartan subgroups, some abelian subgroups of this E8 symmetry. And in principle, I can turn on background gauge fields such that if I integrate like the F, the first chain class, I compute the first chain class on this Riemann surface, I get something, okay? Something non-zero. That's what I mean by flux. Okay, I turn on background gauge fields, which are supported on this Riemann surface. Okay, so in principle, I can turn on those things such that this number is not zero. So for this compactification, what I will tell you now, I don't turn on such things. So all the fluxes are zero. I can turn on gauge fields, but in such a way that there are no fluxes. The fluxes are zero. Okay, and what can be done next is by using this going across the walls and computing anomalies, one can predict what will be the anomalies of the 4D theory. Okay? I take a 6D theory on this geometry, and I want to know something about the 4-dimensional theories that I get. So what is known is the anomalies, for example. Anomalies can be predicted. So the anomalies have the following form. The A anomaly is 75/16 times G minus 1, where G is the genus of this surface, is the number of handles this surface has. And C is equal to 43/8 times G minus 1. Okay? Another thing that you can compute, for example, that we will not use explicitly, are 't Hooft anomalies for this E8 global symmetry. Okay, I don't turn on any gauge fields, so I don't break the E8 global symmetry. So I can wonder what the anomaly, like the 't Hooft anomaly is. For example, trace R E8 squared anomaly is. Again, it can be computed, and it is equal to minus G minus 1. Okay? So it is like we had in 4 dimensions when we discussed conformal dualities. There is some information. There is basically some collection of CFTs that is given to us, but it is not given fully. We don't know everything about these CFTs. We know some information. We know A, C, we know some anomalies, and we know some additional things. Okay? Okay, let me mention that too. Okay, what other things do we know? Like in this example of R0,4 theory of, that I have mentioned, I have told you what are the A and C anomalies, what are the symmetries, what are the 't Hooft anomalies. In that case, there was no symmetries, there were no anomalies, but I also told you something about the operators of that theory. So in this case, what we know, if you compactify on this genus G surface with no flux, there are no relevant operators, no supersymmetric relevant operators. Relevant operators. Okay. In the case of R0,4, we had 66 relevant operators, and then we found a gauge theory which matched that. Here, there are no supersymmetric relevant operators. No matter what genus you have, there are no such operators. If you turn on flux, then relevant operators can appear. It's a more complicated case, but there are no relevant operators. Now, what are the marginal operators, or exactly marginal operators? Okay, so we want to understand what is this dimension of the conformal manifold of the theories you will get. And here the answer is, in a sense, simple. It's a bit intuitive. So the answer is that the dimension of the conformal manifold is 3G minus 3. Okay? What is 3G minus 3? How can you think about it? Did you see this number before? Okay, the 3G minus 3 is what is called the number of complex structure, the complex structures of this Riemann surface. There are various ways to think about it. For example, one way to think about it is you take the stress energy tensor of your 6-dimensional theory, okay, and you KK reduce it to 4 dimensions. There is a mathematical way to do so, using something which is called Riemann-Roch theorem that you probably met in your string theory classes. And what you find that a single stress energy tensor that you have in 6 dimensions gives you 3G minus 3 exactly marginal deformations. Okay? So these are just some parameters which are reduced from 6 dimensions from having a stress energy tensor. There are additional operators that you can have, which are exactly marginal. Instead of starting with the stress energy tensor, you can start with another operator which exists in 6 dimensions. What do you think that operator will be, just from the information that I provided? Okay. I told you that there is a global symmetry, which is the A8. So that means that there is a conserved current in 6 dimensions. So you can do the same procedure for the conserved current, and what you will find that it will produce to you 248 times G minus 1 exactly marginal deformations. What is 248? This is the dimension of E8. Okay? So again, this is we use it as an input to our computation, but if you know your group theory, this is just a dimension of the group E8. It's a pretty large group. Okay. Anytime you will see 248, you should scream 8. If you see 133, what do you scream? 7. 78, 14, G2. Okay. And you can continue. If you know your F4, you can also scream something. Okay. So again, we will in the next lecture, what we will do, we will use this information and just repeat the procedure we did for the G2 in detail. And here we again will do things in detail. And we will find in 4-dimension quantum field theories which have exactly this information. And then because this information will have geometry in it, we will be able to derive easily various dualities and cases of emergence of symmetry, which will be explained by having this E8 in 6 dimensions.